Right, Boolean algebra, that's what we're learning today. So basically, I don't know how to do this, I'm learning this for the first time, so this may or may not be better for you lot to learn it with me, because I can actually teach. So binary systems. Computer systems store and process data as binary digits. So binary digits are, that was a wasp, yes or no, so ones and zeros. So 1 represents there is something there, 0 represents there's nothing. So underneath the surface of computers, the things that process are ones and zeros. So, the transistor. Transistors are electrical components made from semiconductive materials that can act as electrically controlled switches. Transistors can be used to temporarily store data, for example, in some forms of primary storage. And transistors in the CPU. Inside the CPU, transistors are arranged into circuits to perform operations such as calculations when energy is passed through them. Cool. So, transistors are electrical components made from semiconductor materials that can act as something controlled switches. Electrically controlled switches, because obviously it uses electricity to be able to work. So use of transitions, storing data and arranging into arithmetics. Arranging into adder. Nope. Something circuits. What does it say? Adder circuits. Or something else circuits. So arranging into LED circuits. Logic circuits. Oh, so that's literally the next part. So logic circuits. Multiple transistors can be arranged together to make logic gates and logic circuits. Logic gates. Multiple transistors can be arranged together to form more complex switches that only allow electricity to flow through if all or some of the transistors are on. These arrangements are called logic gates. Examples are and, not, and or. So if I were to explain this, this would be, say, like and, not, and or. So say like and had 1 1 0 0 1 0 0 1. Same for and, not, and or. So they all have this start. The and would only return 1 if both values were 1. Not would output the opposite of what's here. So not A would output, say this is A and this is B, it would output 0 1 0 1, and then not B would output 0 1 1 0, and or would output if only one of them is allowing, or if only one of them is true. And logic circuits. Logic gates can be combined to create complex logic circuits. These logic circuits can perform functions such as adding and storing data. And, or, and. The AND gate performs a Boolean add function. It will only output true if both its inputs are true. Simple. Use of transistors in computer systems, storing data, and arranging into logic circuits. Simple. Logic gates are commonly created to perform what type of function? They are commonly created to perform Boolean functions, so true or false, 1 or zeros. Simple. Boolean logic is next. Let's see that. Boolean logic. Boolean operators perform logic operations on Boolean variables and always return another Boolean variable. So AB 0001 11011 and would only output 1. So we've already done this. And, or, not. XOR would mean exclusively or, so it would only return it if one of them are true. So if both of them are true, it just won't work. NOR, that means not and. and means not and nor means not or. And nor, also they've messed up on the titling there, so that's and that's nor, and that is not or, so it's the opposite of what or would give. So which Boolean only takes a single operand, so that is not. Operand is basically like the, this part, that this row would be an operand, operandation. So what Boolean operate 1 or 1 is 1, because there's obviously 1 there. Simple. So evaluating Boolean expressions. To evaluate a Boolean expression, you just substitute all of the values in for the variable and then use the definitions of the different Boolean functions to simplify it one step at a time. So order, you should evaluate any expression in brackets first. Okay, so simple maths, and it's literally truth tables worth showing you. Another method of evaluating an expression is using a truth table, which shows every possible combination of inputs and the resulting output. It's simple. What is the value of and, true and not false? So first of all, it will do not false, which is true, and true is true. So it's possible to describe the various outcomes of a particular scenario using Boolean logic. The outcomes can then be interpreted using logic gates in an electronic circuit. For example, in order to pass an online course, students must achieve 75% in both assessments A and B. So the Boolean logic would be, for A, if your result is, I swear to God I will break this wasp's back with using a pen. So for A, say there were 4 possible outcomes, and for B there are 4 possible outcomes. Then you do the or, now you do the and of it, and then you only get this value, so only one way a student can pass. Example 2. A reef supplement should be added to the calcium level drops below 400 or the magnesium drops below 1300 and the temperature of the water is 24 degrees. Okay then, so this is if the calcium is less than 240 and if the magnesium is less than 330 and the temperature is 24 degrees. So it goes through every possible outcome here and it gives every possible solution. So every solution which returns a 1 you can do. Simple. So a shopkeeper meets a sales target on days where the number of newspapers and magazines sold is greater than 50 or the number of packets of crisps sold exceeds 100, so or. So write this program as a Boolean expression. So sales target met is the final value, newspapers N, magazines M, crisps C. So if the number of magazines, so expression, and because it says or, so expression for newspapers given or. Oh, expression for newspapers and magazine. And then or. I swear to God. I actually can't concentrate. There is a B here and it hurts. Okay, plus. I thought it was a plus, but XY is a plus in the thingamajiggy. Okay, I should probably explain that because the B, stupid B. So sales target is S, newspapers N, magazine M, crisp C. So newspaper and magazine. So newspapers N and magazine is M. So the and is the middle. Then the answer S equals NM. So it's either N and M, but the dot stands for that, or C. So either one of them have to be met. And that's still holding true. True and evaluates true if either or both of the operands are true. That's not and, that is or. You filthy liar. What's the value of not false and not false? What? What's the value of not false and not false? So the not false here would become true. So not false and true would become false, and not false is true. Genius right here. Also because it has two falses, so it's just going to throw you a curveball. When approaching logic or Boolean problems, truth tables can help identify the possible outcomes. So, in order to pass an online course, students must achieve at least 50% in one of the two papers, so that's or. Which of the following expressions describes whether or not a student passes or fails? So this one is or, so it should be this one. Yeah, because it has to be either A or B. Simple. So, now is Carnegie Maps. So Carnegie Maps are diagrams used to simplify Boolean expressions. Drawing Carnegie Maps, solving a two-variable problem using a Carnegie map involves, I swear to God, this. Screen like this. The 0 and 1 down the left of the grid refers to a not A and A. Not A, A. The 0 and 1 on the top refers to a not B and B. Lovely. So now you simplify the expressions here. So in this case you're adding, and then you fill in the table. So obviously here 1 and 0 give 1, 1 and 1 give 1, 0 and 1 give 1, and that one there's nothing here. So the reasoning here is the first of these brackets refer to A and not B. This means if we put 1 in the box with the coordinates A1, BO as shown, the second bracket refers to not A and B. This means if we put 1 into the box with the coordinates 0, B1, the third bracket means A and B. Oh, I get it. Okay, so this basically represents, so now that I've read it and got it, I can actually teach you efficiently. So they've drawn this, and they have drawn this janky looking, oh Jesus, they've drawn this travesty of justice right here. They've made it so this bit's A, this bit's B, and they've made this 0, 1, 0, 1. Oh, you can't see this, can you? Because there we go. But I just swap it around for Seneca. So this bit stands for not A, and this bit starts for A. Same for this, where this is not B and this is B. So in this cube right here, it would be not A and B. In this cube right here, it would be A and B. In this cube right here, it'd be not A and B. And this cube right here, it'd be A and B. I think that is how it works, at least. Not A and not B. Yeah. Okay. So that is it. So in this case, not A is 1 and B is 0. A is 1, not B is 1, so that's 1. A is 1, B is 1, so that's 1, and A and B is 1. Simple. So what expression is represented? So, oh yeah, we didn't read this bit. So group. So the final stage involves grouping the 1s into sets of either 2, 4, or 8. In this example, there are only 1s in total, but they can be grouped into 2 pairs as shown. The green pair have the same value for A, 1, and the blue pair have the same value for B, 1. So the original formula simplifies to AB. So what that basically means is you group these together, then A1 and B1 have the same parts. So it's literally A and B. So here B1 and A1 have the same parts. So it's A and B. Simple. So this is Karnaugh maps are used to simplify Boolean expressions. Simple. So the Karnaugh maps, we can also construct Karnaugh maps to be able to simplify expressions with 3 or 4 variables. 3 variables. With a 3 variable problem, the grid is expanded by adding variables C to the top. This means each column represents a combination of the variables B and C, so in this case, this is basically a truth table incarnate. The second column shows labeled 0, 1. The 0 refers to B, and the 1 refers to C. The order of these combinations follow the rule of grey code. This means each combination is only a slightly bit different to the combination to the other side of it, but just enough. So, this, and then this is here, which you can do with 4. So for 4 variables, you do the same as 3 variables, but instead of this and 1 of these, you just do 2 of these. And then finally, you solve it as you would normally solve it. So, as in this would be not C, not D, not A, not B, etc, etc. And you would solve it. Jesus. So, construct a Karnaugh map for the following expression. A, not B, and B, not A. A plus not B plus not C corresponds to A1, B1, not 1. This is A, not B, not C. So, oh, because A is here. And that goes there, so that's 0. So write the Karnaugh map, write 1 in the square where coordinates A1, BC, 0, 0. B, not A, B and not A corresponds to A0, B1. Write the Karnaugh map, write 1 in the square where x coordinates 0, B is the other way around. I apologise. The something code means that each combination is only a single SHA different from a combination either side of it. Grey code. Grey code. Only a single something different bit. A single bit. And by bit in computer it doesn't mean a smidge, etc. It means an actual bit. So construct something for this. Interpret A and not B. So A is this part. Not B is this one. So AB corresponds to A being 1, B being 0. So write this in the Karnaugh square. Write 1 in the square where coordinates A1, BO. I swear to God, this B or wasp or moth or whatever the hell you are. So not A, not B. So not A is this one, not B is this one. So that's 0, 0. I literally pointed at 0, 0 and just didn't write it. So that was written as AO, BO. AO is popping. A plus B. So that is A1, B1. That's 1, 1. Simple. Write 1 in the square coordinates. That's B1, A1. So A1, B1. Bop. The grey code for 2 digits is 0101, 0010, because this and this would be too far away from each other. And that is, for now, Boolean Algebra.